Okay, well, let's get started. Lights off in 3, 2, 1, lights off. Okay. So I was debating whether to suggest we go outside today. I sort of wish I had now, but I also made a bunch of slides for you that I think will be helpful in understanding the solo model better. So I think we are better off staying inside, even though it's irredeemably hot in here and loud with the fan. This is really a tough situation, and I commend all of you who have asked questions as best you can in this environment. It's hard for me to hear you, and I know it's irritating for you for me not to be able to hear you and all that. So please continue to try to stop me midstream if you don't understand something. Also, with the recording of the class presentations, you'll at least be able to look at them online if you are too weak from heat, like I am right now. To interact with me now, you can also look at the class presentations online and formulate questions as you go. This is really important stuff. This will be on the midterm, guaranteed. Absolutely. The solo model will be on the midterm. And you need to understand it, and more importantly, you need to understand the algebra of the solo model and also the graphing. And I think it's going to be the algebra side that will trip most of you up, because I think that's more difficult. So I've got a bunch of examples in the slides today that I'm going to go through, and please stop me if stuff isn't clear. Problem set 4 is due this Sunday by midnight, and the midterm is in 2 weeks from today in class on Thursday, October 10th. Any questions about the exam timing or the problem sets? Yes. Maybe it is. The question was, is it problem set number 3 rather than 4? Maybe it is. I'm sorry, I don't know. Anybody know? Is it 3? Okay. So that was a misprint. I'm sorry. So I guess it's problem set number 3. It's the next one. I will check that and maybe send out an email. This slide is a little different from the course material today, but I just wanted to put it up there because it made it in back probably in spring 2011, so it's been in my slides now for about 2.5 years. But this is really a remarkable graph. What this is showing is the average wage and salary income by educational group deflated by a price index. So it's the average real wage and salary income. It's what your cash actually purchases. That's the whole story with using a price index to deflate things. And it shows just a very sad story for basically every educational group except for the group that you aspire to join. Those with bachelor's degrees or higher have actually seen increases in their real wage and salary incomes, which is for most of us kind of the main story. The other way, of course, to get rich, and this is probably what a lot of the wealthy people in the U.S. have done, is to make money doing other things than wage and salary income. If you may recall, Mitt Romney was the Republican presidential candidate in 2012 who lost to Barack Obama. He was earning by far most of his money off of capital income because he had worked for, what were they called then? It was Bain, but whether they were a consultant group or maybe they were an investment bank or a venture capital firm, I don't know what they did, but I think the story was that they bought businesses, turned them around, and then sold them for a very hefty profit, and so he was making most of his money in terms of capital income and not wage and salary, and that's certainly a big part of the story. Stay in school, get the degree done. Just because you get a college degree doesn't mean you're going to be making this, but you can't have really a good shot at it if you don't. It's really a remarkable point to make about over the last, in this case, I guess 50 years, not much progress for people further down the educational spectrum. So what we're going to do today with the course material is review the solo model. We'll do graphing, and we'll also do some math of the steady state. And you are on the hook for both of these things in the midterm. And we will not start the Romer growth model. We'll do that next time. My apologies, I should have taken that last bullet off. We're going to do just solo model today. And I think this will be helpful for you because the way I've structured the slides in the class today is focused around two different specific examples of how you might use the solo model to answer an exam question. So here's the first example of an exam question that it showed up in the slides last time if you read ahead. A question might look like this. Suppose there is a new flow of immigration into a country. And what that does is increase labor by some amount delta L from the original amount L up to L prime, which is this higher level of labor supply, L plus delta L. And so you might wonder then what happens to output in the short run and in the long run. And the more difficult question that would be on the exam, so the entire exam question would look like that, and it would have these different parts. It's probably easier to answer what happens to output in the short and the long run. The harder question is what happens to output per person. Recall that output per person is really what we care about. It's the average income or the typical income of the person in the country. So this is a fairly relevant question when one is thinking about the debate over immigration reform. Does immigration raise or lower or not affect output per person? So it's got a very practical component to it, and indeed this is what should be framing at least part of the debate over immigration reform. I'm not sure that it is, but in principle it could be. So it's got some real world relevance. Question? No. So how would one go about answering this? Well, the first thing that you do is you draw the solo model, and on an exam, as you have seen if you've looked at Blackboard and looked at the past exams, I would typically draw for you the axes with K along the horizontal and Y along the vertical. And then I would ask you to draw in these lines. And I've helped us out by drawing in not only the lines, but also the math of what is behind the lines there. So inside the lines, behind the lines, what's the ESPN show? I don't know. Sports. Output Y is actually a function of stuff, right? It's not just output. Output is determined by the level of productivity, by the capital stock to the 1/3 power and the amount of labor to the 2/3 power. And the same is similarly true about the saving curve, that there's all this other stuff down here, right? S times A times K to the 1/3 times L to the 2/3. The depreciation line in econ201 is pretty boring. It's just the number D, which is the depreciation rate, times the level of the capital stock. And this funky-looking purple star is at the crossing of the depreciation and the saving curve, and that defines the steady state level of capital K star. At that steady state level of capital K star, the economy is producing Y star units of output. So that's the deal. That would be, maybe the first question for a total of 4 points if you get all these things correct. You draw in the lines, label them all. Well, what happens when L increases? The key is to look for L in these equations, I think. There are other ways of doing this. You could just think intuitively about what's happening. That will probably also get you to the right place. But I think the most precise and direct way is just by looking at these equations and to see where L shows up. Well, L appears in two places here. It shows up in the output curve, right? Y equals A times K to the 1/3 times L to the 2/3. That's where L shows up. And it also shows up in the saving curve, right? S times Y is equal to S times A times K to the 1/3 times L to the 2/3. So if L increases, it shows up in these two curves. Is this a story about a movement along these curves or a shift in these curves? Well, how do you know? Well, movement along the curves would be determined by some change in the x variable here. So if capital changes, that's a movement along either one of those two curves that is a function of capital. That's not the story that we've got. The story is L is changing, and that must be, therefore, a shift in the curves. So what's this going to look like? When L rises to some higher level L prime, and why? Well, it's because immigrants arrive and they increase the size of the labor force. Then both the output and the saving curves must shift upward. So there are kind of two special things so far about this, is figuring out is it a movement along the curves or a shift in the curves, and then figuring out how many of these curves actually are shifting. And this is going to be different depending on what the question specifies. So it turns out here that if L rises, then both of these things depend on L, as you can see in the map by looking at this. Here's an L, and there's an L. So both of these things have to be higher at every level of capital. Right? Everybody with me so far? Any questions? Now, I think the challenge here is that as you're watching me present this, what I'm saying to you sounds really obvious. I would feel the same way if I were you and listening to this. It's also not helped by the fact that it's very warm in here and I'm practically falling asleep, and you probably are too. This is a little challenging on an exam to figure out exactly which of these curves, if any, are moving. How do you do it? You think about what's going on. Here it's a change in L, and so you look for where L is. If it were the case that L were only up here, then only this upper line, the output line, would be shifting. That's not true, though. It's also down here, so in fact, the saving curve shifts as well. In the short run, the economy still is going to stay at K star in terms of the level of capital. But what's the level of output immediately after the immigrants arrive? Is it Y star or is it something else? So I can't hear anything that anybody's murmuring. Usually I can, and that's a pretty good way to proceed. So let me just try to make this as slow and drawn out and as painful for all of us as possible. I apologize. It's the problem with the fan. So let me restate and work through what you should be thinking in your head. The amount of labor has risen, and that has pushed both of these two curves, the saving curve and the output curve, up. In the short run, the steady state is still, in the short run, the level of capital is still at the original steady state K star. But you can see that in the long run now, there's going to be a new steady state that's up here, right? It's going to be to the right of the original one. And the question I just posed was, with the capital stock still at K star immediately after the immigrants arrive, what is the level of output? Is it Y star or is it something else? And the answer is it's something else. It's not Y star, and it's because the output curve has also shifted up. So in fact, at K star, after the immigrants arrive, you've got the same amount of capital. Think about New York City. So immigrants arrive all the time. You've got the same amount of buildings in the short run. Well, you've got more workers. And the number of workers expanding using the same amount of buildings, it actually produces more output or income. So the very first thing that happens is the economy actually jumps from A to B here in this diagram. Jumps straight up. More factors of production, whether it's labor or capital or productivity. If you increase that overnight, and that's the story, that we've increased labor overnight through immigration, it will increase production overnight. So immigrants arrive, they're productive, we are producing more as a country, then output jumps up from Y star to Y prime immediately. And that's a little different from some of the other stories that we've been talking about, like say, what happens with the change in the saving rate. That's a slower kind of story. This actually happens immediately. Why? Because the output curve has shifted. So we've got the same level of capital in the short run, and at that level of capital, with more labor, we're going to get a higher amount of output, Y prime. Now, are we finished yet? No, because there's this new steady state, so the economy has to be in the steady state in the long run. Visually speaking, where the lines cross is where you have to be ultimately, just like with supply and demand curves. So there's this new steady state at K double star out here. And in the long run, the economy has to transition from Y prime at the original level of capital K star all the way up to Y double star, which is the level of output up here at this point C. Okay? Now, the challenge is, again, having seen enough of these and playing around with it on your own to be able to work with something different that I might ask you about on the exam. Yes? Yeah, the question is K double star the long-term level of the capital stock? And the answer is yes. K double star is the long-term future level, future steady state level of the capital stock. And the way that one gets intuition about what is happening here is the following. Originally, before the immigrants arrived, the labor supply was fixed, the population wasn't growing, and there was a particular steady state level of the capital stock K star. Immigrants arrive, when they come off of the boats or off of the planes, they're just bodies that need capital to be productive. They're just people that work. But over time, immigrants earn their labor income, and they also save. That's the assumption. The assumption in the Solow model is that everybody saves at the rate little s that shows up here in the saving curve. So they are actually saving out of their income and accumulating their own capital. So because we have these additional immigrants who not only are working, they're also saving and accumulating more capital, the nation's capital stock rises in the long run. So the more complicated exam question might be one that asks you, well, suppose immigrants arrive with capital, and that's not inconceivable. That would be a different story than this. Here we're assuming that immigrants arrive, they're just labor, that's all they are. Another story too could be that maybe immigrants arrive and they save out of their income, but they might not invest it in domestic capital. They might send it back to their original countries, and maybe it becomes capital back there. It's not entirely clear. What? Sorry? It would be okay. So the question is, it would not. That story would not be applicable, or vice versa, to this picture. It would be a different picture altogether. Yeah. The implicit assumption here, and I would try to spell this out more concretely in an exam question, is that immigrants are just like us. They show up and they work and they save in the form of domestic capital, and that's why we move from K star to K double star. Suppose you could also say, well, maybe immigrants don't save at all. Maybe they have to consume everything because they're poor. Well, then you would have to model, as an augmentation of this, some reduction in the national saving rate, because the story would be that the natives save at this rate S, but the immigrants don't save, and so the average saving rate for the nation would fall once immigrants arrive, for example. So there are all kinds of different stories one could tell here, and the challenge is trying to just get it all straight and model it correctly. Yes?
In that theory, when the immigrants come and they don't save, so you're reducing the savings rate, you're also increasing the labor. Wouldn't we would need numerical figures for those amounts actually properly depicted, because you're having two changes, so you don't know.
Yeah, it's tough. Yeah. So the question is, suppose I asked on an exam this question of, if immigrants arrive, they supply labor, but they do not save, then what happens? And his question is, well, wouldn't we need to know kind of the sort of numerical size of things? And because you have these dueling offsetting effects. That's correct. I write the answer key for the exam at the same time I write the exam, so I make sure that you can actually answer the question, right? Because the problem is that with a lot of things going on, you might quickly find that there is no obvious answer because of these offsetting effects potentially. That's right.
So the concept, I have it correct, that they would be offsetting.
That's right. So he's asking, if this story were happening, so if the saving rate were falling at the same time the labor were rising, you would have these offsetting effects on the capital stock. That's right. Or on this, I should say, the steady state capital stock, right? And it's not entirely clear what would happen. It's kind of like income and substitution effects with micro, right? It's not obvious kind of what wins in the end. Yes? The question was, do we need to have specific numbers, or will there be specific numbers on an exam, for example, or can we just do this in symbolic graphs? And the answer is, typically an exam question will have both. And I'm going to get to that shortly, that in fact, you can say something quantitatively about things. If I tell you, say, the growth rates, like if immigration raises labor by, say, 10%, then you should be able to take growth rates of the math that I write down for you and then actually find a quantitative solution. Yeah. But typically, that'll be all spelled out for you. So the way I write exams is, I give you the axes and I say, okay, graph it for me. And then after that, I say, okay, now, suppose we know that L actually rises by 10%. Take the growth rates of both sides of this math, and then I write it down for you to figure out what's happening. So it typically lays it out fairly clearly, I think. Now, the thing is that, it is, these exams can be lengthy, they are difficult, they test very different sorts of things. I mean, this graphing and the intuition that might come along with it is very different from the symbolic algebra that we're going to do shortly. You need to know all of it. If you don't, then you get partial credit, and that's okay too. All right, any other questions about this? I'm about to show you then what happens over time with the time plot of output. Okay, so labor increases. The first thing that does is increase output because the blue curve appears. There's an immediate shift up in the output curve. Capital stays the same, but the saving curve has also risen. So there's not only this initial increase in output, but then another increase after that, and we see that here on this graph. So time is along the horizontal axis, output. You could also graph capital along the vertical. Before the time when immigrants arrive, the economy is in steady state. Things are boring with output just equal to y star, the original steady state. When immigrants arrive, and how do you get this graph? Well, you have to have done the previous solo diagram. So if you don't remember it, it can be obviously hard for you to think through this. But in words, what had happened? Well, the immigrants arrived. They immediately increased the output curve. The curve shifted up, and it's because there are more workers around to use the capital, and that produces more output overnight. So there's an immediate jump upward, up to y prime, when immigrants arrive. They're immediately productive. Try not to get hung up with the details that, of course, in the real world, immigrants arrive and they sit in customs, and it takes a while for them to find a job and all that. I mean, yes, but the more time-consuming thing is the process of capital accumulation, by which over the course of a year you divert your resources away from consumption towards saving. You put it in a bank. The bank finds an entrepreneur to purchase a capital good, yada, 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 yada. That's a very long process. That's why this looks like it does up here. There's a higher output level eventually the economy converges to, and that takes a while. So that's the thing that's time-consuming. It's not time-consuming for immigrants to find a job by assumption. We just assume that labor is able to find jobs. And I know that that's not accurate, in the real world, of course, but that, this is a toy economy, and try not to get bogged down in the details. So then there's this new, even higher steady state level up at y double prime, and the reason is, as I said before, we assume that immigrants don't actually bring capital with them. That makes most sense, I think, from a first brush. When immigrants immigrate, they bring themselves and their clothing and maybe some personal items. They don't bring construction equipment and buildings, right? They bring themselves, labor. Other things, though, that they can bring might include things that aren't physical items. They might bring ideas. That's another potential augmentation of this story, maybe on an exam question. You might think about, well, what happens if immigrants bring important new ideas that enhance productive efficiency? And that could well happen. Many immigrants are extremely smart people. They are people who are roughly as smart as me, who compete with me for jobs that I might fill. And there are people who are much, much smarter than me who are immigrants who come over who have lots of new ideas that are useful in production. So ideas could be coming in with immigrants as well, but the first brush here is that they are people. They don't come with capital. They don't come with productivity. They arrive. They have the same level of productivity that all other, say, American workers have. They use the capital stock that we already had at that point. But once they are here, they start working and earning their labor income, and they save, that's by assumption, in the same rate that we do. We have a particular saving rate, so do the new immigrants. That then produces this extra capital that is pushing us up from y prime all the way up to y double star. So the magic here is that this is an endogenous growth model in the sense that it's got endogenous responses of capital. When stuff happens, well, you've increased labor, or it could have happened too, we'll see in a second, but productivity could have risen and done this as well. Capital responds. It's because there's more labor around, and so another way of looking at it actually is the returns to capital are higher because capital is more productive when you have added more labor. So you can spin it a number of ways, and any of those intuitions are correct. I think it's easiest, however, to look at the math of this and work it out that way first. Questions about the graphs before I move on? Yes? Yeah. So the question is about this issue of output increasing immediately when the immigrants arrive. And so you might be asking, why is that the case? And you're also asking, how do you plot it here? Yeah. Yeah. Okay, and so her question is, will it always look like this, or could it look differently with slow growth first and then rapid later? And the answer is, this is the correct way in which growth will happen under these circumstances. It's rapid at first. I don't much care if you, on the exam, draw the sort of the curve part this way. I think you should understand and be able to replicate the part about how there is a jump from y to y prime, and then an increase in some way, I don't really care how you draw it, up to y double star. That's the important part. But the growth up to a higher steady state is really never going to look like what you drew out, like sort of a concave thing that's, that's convex, right? The thing that's increasing at an increasing rate. It's never going to look like that. It always, when you're getting up to a higher point, it always kind of does that. Is it that important? Not really, but it's true. The faster growth happens earlier on, and it slows down as you approach the new steady state. But let me back up and just reemphasize that why does y prime happen at all? It happens because of the particular setups here that an increase in labor shifts this upper output curve, the upper thing in the graph. That will happen if either L increases or if A increases here. Either one of those two things is going to move this upper curve. And that's why there is an immediate jump from this point A up to point B, which is at a higher level of output up there. So that's why, this first part of the graph on the next slide is you need to understand that there is a jump from y star up to y prime immediately. Yes, question? The question is the savings and labor are pretty much the same. The saving rate is the same. Labor has increased. That's the story here. So labor increases from L to L prime. It's a little hard to see that here. It's because we're not graphing labor along one of the axes. But it's happening behind the scenes, and it is why the red curve and the blue curve both exist. Those are higher than their original levels because L has increased. Would output increase as well if savings by itself increase? Let me just back up and remove this to answer your question. Okay, so here's and also forget the title of this as I tell this to you. We're starting off in steady state with this purple steady state star here, and we're at point A in terms of output. Now suppose that all that happens is that the saving rate increases. Okay, so labor doesn't change. The saving rate increases. What happens? How do you answer that? Look at the math. Where is the saving rate? It's only in one of the two places. It's only right here. So when the saving rate alone increases, what would happen is the red line would appear, but the blue line wouldn't. So there'd be a higher saving curve here. That would produce a new steady state somewhere in this vicinity here, a new intersection with the depreciation curve. Over a long period of time, it would raise income in the same way with that upward sloping thing, okay? But in the short run, because all that has happened is the saving rate has increased, in the short run, output would not have increased. Another way of saying that is that the output curve would not have shifted up because only the saving rate increased. So there would be no bump here. I'll just show you that on the next slide. There's no here. This story is about labor increasing, and there's a jump up here. If the story were only about this, my animations are foiling my haste here. If it's only a story about the saving rate, sorry about that. The animations are helpful, but not when I'm trying to speak quickly about an alternative scenario. You would see, the story about output being here, and then the saving rate increases. You would immediately see faster growth in this sort of fashion up to some higher level of output, starting at this point. If only the saving rate were to rise and labor stays the same, you would not see this jump right here. You would only see this part at a lower level. So that would occur down here. Other questions? Okay, now this is hard. What happens to output per person in steady state? And you got to do the math. Graphs, forget about it. Forget about it. You're not going to be able to see this, not in this model with the graphs. And that's a little problematic because, as I said in pitching this, the real world implications really have to do with output per person and arguably the wage. And it turns out that those are kind of related. The wage is actually determined by capital per person, so is output per person. So it's kind of a mathematical thing that we're going to have to delve into. How do you do this? Well, you start with what you know, and you head toward what you need to know. And I think the other tip that I had not thought about in previous terms is this one. Focus on solving for capital. Try to work the math so that you're solving for the capital stock. I think that's what I was always implicitly doing. I just didn't say that in the slides. So what exactly do I mean by this? Well, these are the things that we know. I guess I should have, in addition to this, pointed out that we also know that the second part, delta k equals s times y minus d times k, we also know that that is equal to 0 in the steady state. That's a rather important point. What we need are things like k star, and thus we'll have y star as a function of L in this example. Why a function of L? Well, L is changing in the example with immigration. So we need to find capital as a function of labor, and it's because in the Solo model, it's capital that's a function of other things. Capital is the thing that's responding. It's the interesting thing. So I probably should have written this up a little further so that what else we know is that this is true about the steady state, that s times y star minus d times k star is equal to 0. And I think pretty much it's always going to start then with this very first step of using that last point and rearranging. So if 0 is equal to something minus something else, then it turns out that the two of these things must be equal. That's just the algebraic trick there. And then the next step is to notice that y star is itself a function of k star. So y star is equal to a times k to the 1/3 times L to the 2/3. I've got the stars still, the stars are still out here, it's the Emmys. So y star is equal to a times k star to the 1/3 times L to the 2/3. So all I've done is substituted for what y star is here. And on an exam, do you have to write down the stars? No, you don't have to write the stars. I often skip it, I just haven't skipped it here. It's true that the stars are there because technically, this is only technically true in the steady state, so that's why the stars are there. Not important. Now what? Well, there are multiple ways of getting to the intermediate finish line. The tip here in italics is to focus on solving for capital. We're getting there. This is one equation in one unknown. It's got capital, that's the unknown, And it's got uppercase A and S and L, and those are all known things. S isn't changing, that's the saving rate. A isn't changing, that's the level of productivity or technology. And L is told to us to have increased. It's something that was steady and now it's higher. So this will do it for us in terms of solving for K, but we just need to kind of mess around with it to actually get a formula for K. So solve for K, what have I done? The next line, so in this line now, the next step, I divide both sides by K star. You can do that. You could also divide both sides by K to the 1/3 if you want. Here I've divided both sides by K star, and you can see what happens that K star now vanishes from the right-hand side because I divided by it. K to the 1/3 divided by K is K to the minus 2/3. So this is true. It's not the only way to do the algebra, and you can choose to do it different ways if you want. We are trying to find K as a function of the other thing. So K needs to be on one side or the other on its own, and we're getting there. So now let me click through to the next slide. So what we have so far is this. Now we want to get K star on one side. So let's divide both sides by the other stuff that K star is multiplying. So divide both sides by S and A and L to the 2/3. You'll see something then like this, where I've written L to the 2/3 in the denominator is the same as writing L to the minus 2/3. So that's why L to the minus 2/3 is over here on the right-hand side. Now what? Well, we're solving for K. We've almost got something that looks like that, but we've got this pesky little exponent here. So we're going to raise both sides to the minus 3/2 power, and we've chosen that because K to the minus 2/3 to the minus 3/2 power is just equal to K. Something to a power is something to the product of the powers. So a power function is then distributive too, so D over S times A gets this minus 3/2 power applied to it. L to the minus 2/3 also gets the minus 3/2 power applied to it, but minus 2/3 times minus 3/2 is just also equal to 1. So this is good. I think it's helpful though still to flip the numerator denominator and ditch the minus sign in the power, because this actually is kind of interesting here. This is true about the steady state always in the model. It's telling us that the steady state level of capital increases when the saving rate is higher, other things equal. So here's little s. And if the saving rate is higher, that increases this mathematical formula on the right-hand side, right? And that's intuitive, that if there's a higher rate of saving in the country, then there should be a higher level of capital. That's what this is telling us. Reflexively, if there is a higher rate of capital depreciation, if little d is bigger, what does that tell us about K star? It needs to be smaller, right? So if little d is bigger, K star is going to be smaller. If capital depreciates at a greater rate, other things equal, that means the steady state level of capital will be smaller. And in your head, you can think about the saving curve and the depreciation line. That's a story about the depreciation line being steeper, and it's an intersection that's closer to the origin or at a lower level of capital. So, this math and the graph are actually the same, and you can move back and forth between them. It's just that this is going to get us finally to the point at which we understand what happens to output per worker. So you could, at this stage now, either take growth rates or just eyeball this. The bottom line is that the growth rate in the steady state capital stock is equal to the growth rate of this plus the growth rate of the labor supply. And that means that if S and A and D are not changing, then steady state capital rises 1-for-1 with labor. So if the growth rate in the labor supply is 10%, then capital also rises by 10%. That's kind of an interesting finding that if you have 10% more people, then ultimately you're going to end up with 10% more capital as well. And the reason is these new people who arrive are also saving by assumption. They haven't changed the saving rate. Well, what does that mean about the steady state capital labor ratio? Well, if labor rises by 10%, then capital rises by 10% also. And what does that mean about the capital labor ratio when L rises by 10%? It stays the same. It stays the same because both are rising at the same rate. So the capital labor ratio has to stay exactly the same in the long run. And what does that mean for output per worker? Well, there are a number of ways of seeing what that means, and here I'll show you how to figure it out in one way. Capital labor ratio is the same. What does that mean for output per worker? Well, how do we figure that out? Start with what you know, and again, this is something I would write down on the exam for you. You don't have to memorize this thing, but you do have to know how to work with it. This is the production function. Y is equal to uppercase A times K to the 1/3 times L to the 2/3. We want to know what happens to output per worker. So what we're going to do is divide both sides by L. So that's what we get. The story with algebra is you always need to keep simplifying. So Y over L is equal to this junk over L. So we're going to combine the L terms. So L to the 2/3 divided by L is equal to either L to the minus 1/3 or L to the 1/3 in the denominator. So now, let's combine K over L. That's sort of also a trick here because we have figured out something in terms of the capital labor ratio. So it would be nice to see the capital labor ratio here. We almost have it. Well, it is there. It's A times K to the 1/3 over L to the 1/3, excuse me. With things that are taken to the same power, you can combine these. And we can see through this symbolic math that if the steady state capital labor ratio has stayed the same, then output per worker must also have stayed the same. Because output per worker is equal to A, the level of productivity, times capital labor ratio. If productivity has not changed, and the capital labor ratio in the long run has not changed, then output per worker must have stayed exactly the same. So that's one way of doing this. You also could, you can sort of eyeball it and reason through it this way. You could also have done the following. You could take this math and take the growth rates of both sides and find that the growth rate of output per worker is going to be 1/3 the growth rate of capital minus 1/3 the growth rate of labor. And recall from the previous slide that the growth rate of the steady state capital stock is equal to the growth rate of labor. So something minus something else is equal, something minus the same thing is equal to 0. That would be another way of seeing that the output labor ratio is unchanged. Y over L is unchanged. It's because the capital labor ratio stays the same because capital grows at the same rate of labor. It's all kind of the same way of looking at the same thing. Different way of looking at the same thing, I guess I should have said. Questions? I know there are. You're probably just defeated like I am by the heat and the fans. This is, it's just algebra, but there are tricks involved, and I think you learn the tricks by having seen what we're doing and how we start and where we're headed toward. Solving for capital is a big part of it, I think. Capital is the thing that's endogenous in the model, so you need to find a way to solve for it in terms of the other things that you are told, and then work with what else you know, namely the output function and things like that. Let me also now toss this in. This is related. What about immigration's effects on wages? And I would write this down for you as well, that the marginal product of labor is this math. It happens to be it's the first derivative, but you don't need to know that. It's 2/3 times uppercase A times the capital labor ratio to the 1/3 power. So that is the labor demand curve, it turns out. And you can see that by thinking about what happens when productivity, uppercase A, and capital, uppercase K, are the same. If L increases, the whole thing must decline. And that's a story about this, that as L increases, the marginal product of labor must fall. As you're increasing the amount of labor, holding capital and productivity fixed, each additional worker that you add is less and less marginally productive. They don't give you as much bang for the buck as you increase labor, and the reason is you need to increase capital, or else what's happening is you get this big labor bottleneck. There's too many workers around, and that's the story about this downward sloping demand curve. Labor supply shows up here too. It looks different than what you're accustomed to. It's technically just a vertical line. It is, yeah. We'll see an upward sloping labor supply curve later. But here, this actually is, I guess, sort of important for determining the effects of these sorts of things. That labor just shows up and works, and the intersection of supply and demand is the wage, as you might expect. Well, what happens when immigrants arrive? Graphically speaking, what happens? Immigrants arrive, they increase the labor supply, so this labor supply curve shifts to the right. What happens in the short run then? The wage will fall to some lower wage W prime. In the math, what has happened? Well, in the short run, does the capital stock change? No, it's at whatever steady state was originally. Even though that's not the new steady state, capital takes time to accumulate. So capital is what it was. The story is not anything about productivity changing, so that's not changing either, but labor has increased. So you know that the marginal product of labor, which is equal to the wage, must have fallen, and that's what this graph is showing you. Yes? In the short run, the wage is W prime, right? That's the very first thing that happens. The immigrants get off the boat or the bus or the airplane, and they supply their labor, and in the short run, that reduces wages in the receiving country. Now, in the real world, what's happening is that different immigrants compete with different types of workers. It is possible that you may not be competing with many foreign-born immigrants yourselves, but at the high and the low end, there's a lot of competition. So people without a high school degree compete with foreign-born workers quite a bit, and this is documented that people without a high school degree see their wages fall because of low-skill immigration. It's probably also the case that people at the high end of the distribution also compete with foreign-born workers and see their wages decline. So that happens, and it's a big issue, probably the biggest issue really for low-income Americans without a college degree, probably without a high school degree. This really does happen. Immigration will reduce the wage in the short run, but the story isn't done yet, because as we have seen over the last several slides, that if immigrants arrive, provided that they save out of their income in the same way that native-born workers do, that will increase the capital stock. Well, what does an increase in the capital stock show up as in this graph? If the capital stock increases, how do we depict that here? It turns out that that's going to be a shift in labor demand. So the labor demand curve is given by this math of marginal product of labor. And by assumption, we're holding productivity and capital fixed. If capital increases, though, it makes workers more productive at every level of labor. So that's a story about an outward shift in the labor demand curve. And now there's some extra sort of hand-waving trickery that I'm about to say. Well, we have already seen that capital per worker returns to its original level. That's what we figured out a couple of slides ago. The steady state level of capital rises one for one with labor, it turns out, in the Solo model. A really special thing, but it's because of the assumption that workers, foreign or domestic born, whatever, save at the same rate. So we know actually that we're going to end up back at W star in the long run. Kind of a magical thing, but we know that because we worked out the math. K over L returns to the same level. So we have to get back to the original level of the wage. So that's why we know that, in fact, the labor demand curve shifts out to exactly this point out here. Now, this is a toy model, but it's really not at all a bad perspective on real-world types of things. Immigration really does, maybe not disrupt, but it changes domestic labor markets. It does. It's an increase in the supply of available workers. And mechanically speaking, this logic is correct. It just may not be the full story. But the logic says that an increase in the amount of labor is going to reduce the wage, at least in the short run, and here it does. It's just that what happens over the longer period of time is that we return to, well, we transition toward a new steady state. In so doing, capital is accumulated and actually pushes labor demand out again. So wages return to where they were. And ultimately, there's kind of no effect on wages in the long run here. Okay, questions? Intuition, what's happening? When a finite number of new immigrants arrives, it turns out this is a little bit different if instead of a finite number, we're talking about a steady rate of growth of the population that is provided by new immigration. But that's not important here. That's an econ201 kind of thing. When a finite number of new immigrants arrives, they represent an increase in labor alone by assumption. We assume they don't bring technology or capital with them. And in the short run, an increase in labor increases production, but because capital is fixed in the short run, capital per worker and thus output per worker and also the wage all fall in the short run. So this is why it's maybe a little dissatisfying that the textbook and my slides have the Solow model set up in terms of levels of things, output, rather than output per worker, because in fact what we probably care more about are things like the wage and output per worker rather than the level. That's kind of a challenge here, I guess, to kind of pick out the things that really matter in the real world out of this larger apparatus. In the long run, though, our assumption is the immigrants save just like natives, and that raises the capital stock. So the magic is the capital per worker returns to its old level, and you can make this intuitive by thinking of the following, that saving per worker is unchanged by assumption. That may or may not be true in the real world, but we assume that it's true here, that every worker, regardless of nativity, saves at the same rate. And so that produces a certain amount of steady-state capital per worker, given the depreciation rate doesn't change. And so in the long run, capital per worker, output per worker, and the wage all return to where they originally were because we haven't changed. Kind of the key element here is the saving, and the saving rate is the same. So the size of the labor force doesn't really matter much in the simple Solow model. All right, moving right along. Everybody looks tired and hot and defeated, and I sympathize with you. I'm most of those things too. What's important for you, we're going to do another example after this, but I just thought I'd toss this in there in case we don't finish it this class. The important things for you in the Solow model is thinking about, if something happens, which curves shift, if any, when something happens, when X happens. And it could be the case that none of the curves shift. Remember that last class we talked about the effect of an earthquake that destroys capital, but doesn't kill anybody, and it doesn't change technology at all. That would be an example in which none of the Solow model curves are shifting. It's just a story about a reduction in capital. That's all. So it's not always the case that curves have to shift. But as we have seen, it's sometimes the case when one curve shifts, and sometimes two curves may shift, and things can get even more complicated as well. If the question asks about numeric predictions or specific things that you cannot see in the basic diagram, then what you do is you start with what you know, and in the Solow model, that's two things. I should have written the part that this equals 0, that sy minus dk equals 0 in the steady state. That's rather critical. I should have written that here. And remember that the production function is this, and to remember to substitute. So I'll always write this down for you on the exams. You don't have to memorize these, but you do have to be able to work with them. And so the key point here is that y shows up here, so you can substitute into this formula with that relationship, and you typically solve for k as a function of s, d, and a, and think about what you need to ultimately find out using those tips. Okay? Hot, defeated, sad that we're doing this, all kinds of things. Now, let's be optimistic. You guys mastered this already. This is awesome. Great. All right, because then you wonder, well, what is this good for? Well, it's mental gymnastics. That's why you're here. That's why you're in college, so that you can adapt to changing job market conditions through mental gymnastics. All right, so let's do more hideously boring solo model stuff, and maybe I can trick you into a wrong answer. I don't know why we always focus on that, but it's to try to poke your creative thinking and to get you to think quickly on your feet about things that we're not born knowing. That's kind of the weird thing, I think, about human brains, is that why are we here? Well, we're here to try to exercise your brain, to get it to do things you're not accustomed to doing with it. It's wild how we are able to do that, ultimately, and do interesting things. Okay. So let's start over, and suppose instead of a story about labor, let's suppose instead that a technological breakthrough increases productivity, uppercase A. And the story might be something like a new farming technique that allows farmers to produce more wheat per hectare or whatever unit it is of dirt that of farmland that they're using with a particular amount of capital. So they have a new technique, a new way of, say, planting the seeds or tilling the soil that somebody has learned through trial and error and disseminated this knowledge. And so the knowledge about how to produce more with what you've got is something everybody can use, and it increases productivity, which is the uppercase variable A. Well, before the increase in productivity, the solo economy is a K star. Y star, the original steady state. What happens when A increases? And just like before, the key is to look for where A is in these equations. You could also try to make the intuitive jump and figure out what things change. So what's the story here? Uppercase A, the level of productivity, actually appears twice, just like L does. So it appears in the production function, in the output curve up here, and it also occurs down here. It appears in the saving function. An increase in productivity increases output, and at a constant rate of saving, it also increases the amount of saving. So the story then, with the change in the level of productivity in the solo model, is the following: that the level of productivity A rises to some higher level A prime, and just like before, both of the output and the saving curves shift upward here. An increase in productivity makes capital and labor, which are in the short run in the same amounts. So we're still at capital equal K star in the short run, and the labor that we've got is still whatever this level L happens to be. It makes it more productive. It makes them, I should say, more productive. Capital and labor become more productive overnight. So in the short run, the economy's capital stays fixed at K star, but at K star, output is now higher because of the increase in productivity. There's a new production technique that all farmers are able to use. So given the amount of capital that they have and the same number of farmers, they are more productive, they produce more output, and because the saving rate is the same, they also actually are saving more. Output jumps up overnight because of the production technique increasing. So the economy moves from A to B, output jumps up. And there is a new steady state at K double star here to the right. So visually and in some sense qualitatively, everything that we saw in the previous example with immigration is also happening here so far. Do you think anything might be different, though? Is adding productivity and adding labor the same thing? Obviously not. Well, how do you think is it going to be different? Here it looks exactly the same, basically. So, you know, we're going to see this long-term transition to a higher level of output up here at point C. So productivity adds, I've got to draw in here. It adds productive capacity, just like labor, an increase in labor does, and we're going to be better off in terms of our national GDP. That's what's along the vertical axis here. So hang on to that thought about how it might be different. So what does this story apply about output over time? And it's going to be exactly the same picture that we saw before, but the stories behind these events are a little different. So there's this time when productivity increases, that's along the horizontal axis here. Before productivity increases, growth is 0 and output is steady at y star. When productivity increases, that immediately improves the production possibility. So output jumps up to some y prime, again, just like it did before. And then the economy converges to this new higher steady state level after that. But the reason why it does is subtly different. So what's happening here is not that there are more people, immigrants, saving at a particular rate and providing more saving. There's the same number of people here, but they have more technology. And what happens is that the increase in technology, or the improvement in technology, increases production possibilities across the board, but in particular it increases them right now. And because output or income rises immediately, so too does the amount of saving given the constant saving rate. So the same amount of workers are now producing more output, and they are able to save a larger amount in levels of that because they're saving at a particular rate. That's the assumption. Now, you might step back and question that assumption. You might say, well, if I'm a worker and I notice, wow, I'm suddenly much more productive, and I'm producing so much more, say, corn off of my farm each year, and I have been saving 10% originally of my corn. Well, I'm so much more productive, and what do I use corn for? Well, I use it as seed corn to produce the next year's harvest. If I'm suddenly more productive, my output has increased by, say, I don't know, 20%. What might you do to your saving rate? You might actually lower it. I don't know. I mean, it's not entirely clear. You might set aside less seed corn and just eat more corn this year and get fat and enjoy it. I mean, it's fun to eat, right? The assumption in the model, in the Solow model, is that unless I tell you otherwise, the saving rate stays the same, and because of that, when income increases, so does the amount of saving, and so that's a new amount of capital. Let me just show you that in the previous graph. We've got the same amount of people, and in this Solow diagram, what's happening is that productivity is rising, and that pushes both curves up. So we've got the same amount of people, but now we've got an increase in the amount of saving, represented by the difference between the level of the red line at K star and the purple point here, the purple star. So an increase in productivity increases the amount of saving that's around, and that ultimately gets us up toward this higher steady state. So graphically speaking, it's the exact same story, but narratively speaking, if that's a word, the way I narrated it was very different. It's not about people saving and there being more people around, you get more saving. It's a story about a transition to a higher steady state because of an increase in productivity or technology. Yes? The question is, how does the long run differ from the short run? It depends. What do you mean by differ? So I think you're asking that whether this scenario and the one in which immigration happens, if both those scenarios result in higher income. Is that what you're asking? And the answer to that would be yes. Yeah. Okay, so I think what you're asking is, what is the short term or short run, and what is the long run here in this example? Okay. The answer is the short run in this example is the jump from point A to point B. So in the short run, overnight, technology improves. Somebody finds a new way of harvesting wheat or planting it that really increases productivity. They tell everybody about it, and the very first thing that happens is output increases, the economy jumps from A to B, capital is fixed in the short run. But in the long run, what happens is that because of this jump from A to B, there's more income, there's more production. At a constant rate of saving, that means there's also more savings, you could call it that if that helps you. There are more resources that are becoming new investment that pushes us in the direction from B to C, from K star to K double star. So the long run is the motion in that direction. It's toward the new steady state at K double star. Yeah.
With regards to wages, since we now have a higher output with the same level of workers, wages would actually rise in this scenario below.
Yeah, I think that's good intuition. So just to repeat what he said, what I see here, he's saying, is that output has increased, I know that, and that labor has not increased in this scenario. So it stands to reason intuitively that because output per worker has increased, so too has the wage or labor earnings per worker, you could view it that way. That is true. It's the intuition, and you're right about it, but we haven't technically shown that yet. So that's the next thing I wanted to turn to. We've got about 8 minutes, so I think we'll be able to see that. Let me just pop out and zip ahead over the next time diagram and show you the math of what we're going to do. The questions are, what happens to output per person? The wage is also important, and I think I've got that in here as well. So that, again, is a problem of the math. And so I think if I asked you what the output per person was or what had happened to it, I think you could say, without a doubt, well, qualitatively it's higher, right? Done. And that would be a perfectly sufficient full credit answer on the exam. If you're wondering what happened to the wage, that's a little bit of a different question. And it turns out that the wage is a function of the capital labor ratio. So I guess you could also say, well, qualitatively, I have seen that the capital stock has increased and the labor has stayed the same, so therefore the wage is higher. You could do it that way too. But there is a little bit of a distinction there. Those are slightly different. Let's just look at the math again. It's the same kind of story. This line is different, though. What we're looking for technically is K star as a function of A. That's the thing that is changing in this example. The same, though, as before, we work with what we know, which is that the steady state math is that S times Y minus D times K is equal to 0. That is that they are both equal. And just like before, we're going to substitute for output. That's the thing on the left-hand side now that's multiplying the saving rate, and now we're going to divide by K star. You can do this a number of different ways. You're solving for K star, and since we're kind of running short on time, you have seen this before, so I'm going to go rather quickly through it. We're basically at the same finish line here. Now, at this point, what do we do? Probably it's best to now take growth rates. The problem is, we've gotten to this same finish line with the algebra, and I apologize for zipping through it very quickly, but it's exactly the same algebra as we have seen in the previous slide, that K star, the steady state level of capital, is equal to this weird S times A over D to the 3/2, weird thing, and then times the level of labor. In the previous slide, we could kind of stop at this point because it's sort of obvious that capital rises 1-for-1 or linearly with labor. The question now, though, is, well, what happens when labor isn't changing, right? That's our scenario now. A is changing. Uppercase A, the level of productivity is changing, and what does that imply then about capital? Well, let's take growth rates. Again, here you could do this a number of different ways. I think this was helpful for review. Take growth rates of both sides. Well, the growth rate of K then is equal to the growth rate of this beast here, this S times A over D to the 3/2, plus the growth rate of L. That's the first thing. Now let's simplify further by pulling out the power there. So the growth rate of S times A over D to the 3/2 is equal to 3/2 the growth rate of S times A over D. And then GL is still in there. It's going to be 0 in this example, but let's just keep it around for a while. Now what? Well, let's take the growth rate of this inner ratio. S times A over D. Well, the growth rate of S times A is equal to the sum of the growth rates of S and A. And then the growth rate of a ratio is the difference between the growth rates. So I've kind of skipped a step here in showing you that the 3/2 times the growth rate of this beast is equal to 3/2 times the sum of these things, GS, the growth rate of the thing in the numerator, plus the growth rate of the other thing in the numerator, minus the growth rate of the thing in the denominator. And all that is multiplied by a 3/2, and then there's a plus GL is still there. So this looks pretty messy right now, but remember that in this example, the only thing that's changing is uppercase A, the level of productivity. So a lot of this stuff is 0. If A is the only thing that's changing, then the only thing that's left is going to be the 3/2 times GA. All right. Doesn't seem like we've made much progress, but in fact we have. What we've seen here is that when A increases, when productivity increases, say by 10%, then capital increases by, well, this is a little surprising, by 15%, by 3/2 that growth rate. So capital increases by even more than the increase in productivity there. Capital responds by quite a bit. It's the magic of, or bang for your buck, if you will, of productivity growth. Okay, so let's try to remember this, that capital is up 3/2 times the growth rate of A. So remember from before, and you can start in various places, but I just thought I'd start with this from before. You can also now take growth rates of this to see how output per worker varies with the level of productivity. Well, the growth rate of both sides of this then is going to give us the growth rate of Y over L, and just leave it at that, because what we want is the growth rate of this ratio. End of story, so don't simplify that part. What's on the right-hand side, it's the growth rate of A plus the growth rate of the thing it's multiplying. Well, now what? Well, there's a power here, right? So now use the power rule. That's then equal to 1/3 the growth rate of this ratio. And here I've written it a little differently, right? So the growth rate of Y over L is now the growth rate of A. That's something that's changing, right? A is changing, so there's a growth rate of A happening. But now notice what's going to happen over here. Well, L isn't changing, but K is changing. What do you need to do next? Simplify again. The growth rate of a ratio is, I'm sorry, that's a misprint. It's the difference of the growth rates. I'm sorry, I'll correct that. This should be a minus sign, sorry. Yeah. It turns out not to matter why. L isn't changing, it's GL is 0. So I'm sorry, I totally biffed that one. It happens, and if you biff something like that on the exam, you know, you get partial credit. You get like a point off for biffing a plus or minus sign. I do it all the time. I did it right there. It happens, right? So what is changing? Both A and K change because K is responding to A, but L is not changing. Its growth rate is equal to 0. Now, this is where we use the previous slide's insight that the growth rate of the capital stock is 3/2 the growth rate of A. So substituting, what we're finally finding out is that the growth rate of Y over L, which is the growth rate of A, that's now here, plus 1/3 the growth rate of capital. Well, what's that equal to? Well, it's 3/2 the growth rate of A. It's this thing. And then minus, it should be, and I'll fix that, to 1/3 the growth rate of L. That's 0. Well, that might make your head swim a little bit, but if 1/3 times 3/2 is equal to 1/2. And so what we're ending up with is this. The growth rate in output per worker is 3/2 the growth rate of productivity, whatever that might happen to be. And the bottom line is that productivity growth raises income per person by quite a bit here. So I know you're tired and we've gone a long, long way, but let me try to summarize what we found here. It's very different to have an increase in labor than to have an increase in productivity. And this is one big way in which it matters, that output per worker, and it turns out also the wage increases. Output per worker rises with productivity in the long run. It does not rise in the long run with immigration. Productivity is a very good thing. And that's where we're headed next time with Chapter 6. All right, so thank you. Thank you for bearing with me. Lights on, 3, 2, 1, lights on.